So where we usually enter the conversation is when someone comes to us and they have a chemical they want to produce. But to do so with man-made chemicals and materials would be too complicated or too dirty or too costly. And so they turn to enzymes. And enzymes for these sorts of problems are often a great solution because these are the materials that nature has evolved to control chemistry in living organisms. So there are several attributes that really make them tailor-made for this sort of problem. They can be very efficient. We'll talk about each of these in detail. They can be highly specific. They're multifaceted, and they're genetically encoded. So first, let's talk about efficiency. As Akbar alluded to, there are enzymes in the world that catalyze reactions that by themselves would spontaneously happen over the course of hundreds of years, but they can be catalyzed to produce the same amount of product in fractions of a second. So this makes enzymes incredibly useful if you want to get more product in a reasonable amount of time from your process. They're also catalysts, and that means by definition, they're neither produced nor consumed by the processes that we use them for. This means that a relatively small amount of an enzyme can be used to make a very large quantity of product, and it isn't without needing to be replenished. Enzymes are also highly specific. So they have an active site. This is where the chemistry happens. So this will be something that's specific for the molecule that the enzyme is meant to act upon. That's called its substrate. So here the active site of the enzyme will only fit a specific molecule, that substrate. And once that substrate lands in the active site and forms this enzyme substrate complex in the center, only a specific type of chemistry will happen. So there will be a certain chemical bond that's made or broken at the active site, and then those products will be released. However, an enzyme is more than just that active site. So they can do more than one thing at a time. Here, we've kind of schematically drawn an example of a cellulase. This is a very well-studied enzyme. Cellulase has that same sort of active site. Here it's called the catalytic domain, CD. But it also has this carbohydrate binding motif. So the catalytic domain is specific to sugar subunits. What the cellulase does is it sits on a cellulose fiber, which is the substrate, and it chews up that cellulose and releases sugar subunits into solution. The catalytic domain itself would successfully cleave and release one or two or more subunits, but it's linked to this carbohydrate binding module. The carbohydrate binding module sticks to that fiber and basically feeds more sugar subunits into the catalytic domain. This allows the cellulase to be highly processive, meaning that it can produce many, many molecules of sugar from one attachment event to that cellulose fiber. So working together as an integrated machine, this single enzyme will specifically cleave and produce one type of product many, many times without needing to reattach to that cellulose fiber. And the final attribute that we take advantage of here is that all of these enzymes are genetically encoded. That means everything we've talked about so far, that catalytic efficiency, the specificity, and the multifaceted nature, so the different domains of an enzyme, they're all controlled by the A's, T's, C's, and G's in the DNA sequence of the enzyme. So that DNA encodes different amino acids. There are 20 naturally occurring amino acids. So if you just wanted to think about how many combinations of a single amino acid protein there were, you would have 20. If you thought about how many pairs, it's 20 times 20 squared, so that would be 400. These numbers get very large very fast, right? So a typical protein might be 300 amino acids long. If you wanted to think about the number of combinations of amino acids in that 300 amino acid protein, it would be more than the number of atoms in the universe. So we can't experimentally test every single one of these possibilities to find the best one. And this is really where Allozymes can accelerate this whole process. So we use directed evolution. So we start by designing libraries for a given target enzyme. And those designs can be from a number of different concepts. One that's design free is called a scanning library. So that's where we take every single substitution possible and we do it one at a time across the amino acid, across the protein sequence. We also can look at sites that might be near the active site, or we can look at amino acid residues that are evolutionarily conserved in related enzymes. Or we can use more AI-driven approaches that'll actually be the subject of a whole different webinar. But we can make libraries along each of these different types of concepts, might have 5 different flavors of enzyme libraries. We can then order the DNA to experimentally build those in the lab. And then we construct those. Maybe you construct 5 different enzymes in a week, enzyme libraries in a week, each containing maybe something on the order of 1 million different enzyme variants. And then we can use our microfluidics platform, which Patrick will tell you about in just a minute, to test each one of those libraries. And this is the key. So maybe some of those libraries are duds. Maybe we didn't have any good enzymes in that pool. AI is getting better every day, but there's still a lot we can't predict. But the key is that we can build multiple enzyme libraries and we can screen them very quickly and deeply. And we can see which concepts, was it maybe that active site concept, or maybe it was the evolutionarily conserved concept, but which one really lit the fire under our enzymes. And then we can select the best enzymes, and then we can validate those enzymes using standard analytical chemistry approaches like HPLC or gas chromatography. So in this manner, we can really accelerate the process of directed evolution and get to the enzyme that's going to be best for our process.